The Nobel Prize in Physics has always celebrated those who unlock the universe's secrets: atoms, light, space-time. For over a century, it has honored the explorers who dared to ask the biggest questions about reality, rewarding discoveries that changed how we see the world at its most fundamental level. But in 2024, the world was stunned. For the first time, the prize went not to a discovery about the physical world, but to artificial intelligence, a field that bridges the gap between machines and minds. This wasn't for inventing a clever gadget or a faster computer. It was for a radical idea. That thought itself could be understood as a physical process, governed by the same laws that shape the universe. John Hopfield and Geoffrey Hinton asked a daring question. What if memories and ideas are as real and measurable as magnetism or gravity? Could the patterns of our minds be mapped and studied like the forces of nature? Their groundbreaking work blurred the line between mind and matter, revealing that intelligence is not just a human trait, but a phenomenon governed by the same fundamental laws as the cosmos itself. The brain, they showed, is a universe in miniature. This wasn't just about computers or robots, it was about the universe building thinking machines, us included. It suggested that intelligence could emerge wherever matter and energy are organized in the right way. The prize marked a true paradigm shift. Understanding intelligence is now inseparable from understanding the universe itself. The boundaries between physics and thought have begun to dissolve. Are we truly unique, or is intelligence simply an emergent property of matter and energy, waiting to arise wherever the conditions are right? The question now echoes through science and philosophy alike. The story of the physics of thought has just begun. As we turn this new page, we find ourselves at the threshold of a deeper understanding, one that may redefine what it means to be alive, to think, and to know the universe. To grasp this breakthrough, let's start with something familiar: a magnet. Imagine a grid of atomic spins, each one a tiny arrow, influenced by its neighbors. These spins can point up or down, and the way they interact determines whether the magnet is strong, weak, or somewhere in between. The behavior of these spins isn't random. It's a dance, a negotiation as each spin tries to align with those around it. This collective alignment, described by the Ising model, is a system seeking its lowest energy, its most stable state. The Ising model, a cornerstone of physics, shows how simple rules at the smallest scale can lead to complex, organized patterns. It's a beautiful example of order emerging from chaos, as the system naturally finds harmony. In 1982, John Hopfield saw a remarkable parallel: replace spins with neurons, and you have a model for memory. He realized that the same mathematics describing magnets could also describe how our brains store information. Neurons, like spins, can be on or off, and their connections act as peer pressure, nudging each other toward certain patterns. Each neuron's state is influenced by the activity of its neighbors, just as each spin is tugged by those around it. A memory isn't stored in a single neuron, but as a pattern, a stable configuration across the network. When the network settles into one of these patterns, it's as if the memory has been recalled, the system finding its own version of stability. Learning sculpts these connections, making certain patterns, the memories, more stable. Over time, repeated experiences strengthen the pathways, so the network is more likely to settle into those familiar patterns. Recalling a memory is like giving the network a hint. It settles into the complete pattern, just as a magnet aligns its spins after a gentle nudge. Even a fragment of information can trigger the whole memory to emerge. This is associative memory. A partial cue triggers the whole. Our brains are designed to fill in the gaps, to complete the picture from just a few clues, making memory both robust and flexible. The Hopfield network showed that memory is a physical process, not a filing cabinet. Memories aren't stored in neat, isolated drawers, but woven into the fabric of the network itself. Geoffrey Hinton expanded this with the Boltzmann machine, adding randomness, allowing the network to escape shallow patterns and find deeper ones. This randomness helps the system avoid getting stuck, exploring new possibilities, and learning more complex associations. The physics of matter became the physics of mind. The same principles that govern the tiniest particles now help us understand thought, learning, and memory. Intelligence, it turns out, is a dance of energy and stability. Our thoughts, memories, and even creativity emerge from this dynamic interplay. The same principles that govern magnets also govern memory. The universe's rules echo in our minds, connecting the physical and the mental in surprising ways. The universe, through us, is learning to remember. Our brains are not separate from the cosmos, they are its latest experiment in pattern and memory. The boundaries between physics and thought are dissolving. What once seemed like separate worlds are now revealed as reflections of the same underlying order. This is the cosmic connection, a bridge between the laws of nature and the mysteries of the mind, showing us that in the grandest sense, we are the universe thinking about itself. Picture a landscape of valleys and peaks, an undulating world shaped by invisible forces, where every rise and dip tells a story. This is the energy map of a neural network, a living terrain that encodes knowledge, memories, and possibilities. Each memory is a valley, a stable, resting place where information settles, protected from the chaos above. Teaching the network a memory carves a new valley, making that pattern easy to find again and again, deepening the groove with each repetition. A scent, or a blurry image, is like a marble on a slope. It rolls into the nearest valley, the full memory, guided by the shape of the land beneath it. Memory isn't static, it's recreated each time by the network settling into harmony, the landscape subtly shifting as new experiences reshape the terrain. Hinton's Boltzmann machine introduced randomness, letting the network jump out of shallow valleys to find deeper, more meaningful patterns. Sometimes a little chaos is the key to discovery. This mirrors creative thinking, making new associations, forging connections between distant ideas, and building bridges across the landscape of the mind. The energy landscape is sculpted by experience, molded by every moment, every lesson, every memory that leaves its mark. Learning is physical. It shapes the network structure, rewiring connections, thickening pathways, and altering the very fabric of thought. Memory is dynamic, not a lookup but a process, constantly in motion, always adapting, never truly at rest. The mind is a system seeking stability, just like any physical system, always searching for balance in a world of change. The physics of thought is the physics of the universe. Energy, matter, and motion, all intertwined in a cosmic dance. Our brains and our machines are both sculptors of energy landscapes, shaping the world within and the world without. Intelligence emerges from this dance, a harmony of structure, randomness, and experience, sculpting thoughts into existence. The leap from magnets to memory led to an even bolder idea: neural networks and quantum fields share deep mathematical roots. In physics, reality is made of fields: electron, photon, Higgs, vibrating across space-time. Particles are just excitations in these fields. As neural networks grew to billions of connections, their collective behavior began to mirror the equations of quantum fields. The random fluctuations in a vast AI network behave like quantum fluctuations in the vacuum. This isn't coincidence. It means a large neural network is a kind of synthetic universe. Its properties echo the fields that make up reality. In building artificial brains, we've created pocket universes in silicon. The line between simulation and reality is blurring. This discovery isn't just philosophical, it's practical. Physics and AI now help each other. AI can simulate quantum systems too complex for traditional computers. Instead of calculating every interaction, we train neural networks to learn the system's behavior. The AI becomes a simulator, predicting quantum experiments at unprecedented speed. Like weather models, neural networks capture large-scale patterns without tracking every detail. AI learns the statistical essence of quantum fields, becoming a new kind of scientific instrument. It lets us explore scenarios too complex or extreme for labs. AI is now a window into the heart of physical law. AI is revolutionizing physics by finding shortcuts nature itself uses. Both the universe and neural networks seek the most efficient, lowest energy states. This shared principle makes AI a powerful tool for discovery. In material science, AI predicts new compounds by learning the rules of chemistry and quantum mechanics. It can scan millions of possibilities in hours, suggesting novel materials for batteries or superconductors. In particle physics, AI sifts through torrents of data, spotting rare events that might signal new physics. It acts as a creative partner, expanding what's possible. AI is now essential in mapping the universe's building blocks. It accelerates discovery, guiding us to breakthroughs. The tool is now part of the scientific process itself. AI and physics are intertwined, each advancing the other. The cosmos is being explored by thinking machines. The universe is noisy and signals are often buried in static. AI has transformed our ability to extract faint signals, like gravitational waves, from overwhelming noise. Neural networks learn to distinguish the subtle chirp of a black hole merger from random vibrations. They act as expert listeners, revealing cosmic events with clarity. AI sharpens telescope images, finds exoplanets, and processes astronomical data with unprecedented precision. Across astronomy, AI is our new set of eyes and ears. It lets us perceive the universe with clarity once thought impossible. The cosmos is now more accessible than ever. The fusion of AI and physics is driving the next technological revolution. In quantum computing, AI helps stabilize fragile quantum states, acting as a guardian against noise. Machine learning algorithms design, control, and protect quantum devices, moving us closer to fault-tolerant quantum computers. AI optimizes quantum sensors and interprets their complex data, pushing the limits of measurement. In quantum cryptography, AI manages secure networks, ensuring unbreakable communication. From simulating quarks to building quantum tech, AI is the essential toolkit for modern physicists. The 2024 Nobel Prize recognized this new scientific method. Physics and AI are now inseparable. The tool has become the engine of discovery. We've come full circle, from a surprising Nobel Prize to the unity of mind, matter, and the cosmos. Intelligence is no longer mystical, it's a physical property, an emergent phenomenon from complex networks. Thoughts and memories are patterns in an energy landscape, shaped by the same laws as stars and galaxies. This view grounds consciousness in the fabric of reality. The universe itself may be an information processing system, physics as the algorithm, matter as the hardware. Building AI is tapping into a process as old as the cosmos. Our models speak the universe's native language. The 2024 Nobel Prize marks a future where physics, AI, and neuroscience merge. We are thinking matter, the universe contemplating itself. The boundaries are dissolving. The story of intelligence and the cosmos is just beginning.